Hello, everybody. I know there was forum topic where we were talking about magnitudes, and it started getting into eye response. And I thought maybe this is a good topic to go a little deeper. This is not something I normally cover in this course, but I think that it is important to understand a little bit more about the behavior of light, as well as what we're actually trying to measure, and how different circumstances or different star types, different star characteristics can affect how your eyes work and the measurements that you're actually taking, because better understanding of that, leads to you being a better observer just by being conscious of what's going on. And it's one thing I had to learn a couple ways the hard way. My mentor, when I first joined the AAVSO, helped me understand some of these things a little better. But I'm going to go a little deeper into some topics here, and hopefully it can be beneficial to you to understand what's going on a little better. So let me share my screen here. And so, yeah, one thing that I always like to do when I do outreach with my telescope, and I take it out, and if it's the summertime, I'm going first to Beta Cygni. It blows people away how stars can have such different colors, because when you look up the night sky, there's such observation bias that we only see the brightest, which tend to be much bluer, whiter stars, not the deep red ones. But when you're a variable star observer, as we'll find out, most of the stars that we deal with are very evolved, very cool, and very red. So that does have effects on your eyes. So if you break it down exactly to what a star is, fundamentally is a black body radiator. Now, this may be a term that you may not be familiar with if you didn't study physics in college, as I did, but a star is a purely radiative body. It's almost a pure or perfect radiator, the best ones that we know of. Everything that has, and so the concept here is everything that has temperature emits light of some sort, right? I'm emitting light right now. You're emitting light right now. Anything that has a temperature that's above absolute zero is emitting light. Now, our eyes just aren't sensitive to it. So, my body temperature is what, 98 degrees or so. So I'm emitting light, but it's deep into the infrared. And that's why night vision goggles, if you change your eyes from being sensitive to optical light to infrared light, like soldiers do when they wear their night vision goggles, all of a sudden people start becoming very bright. So if you look at the concept of a black body radiator, things will start, you got to get around 500 degrees at least before it becomes hot enough to start emitting light into the visible regions of the spectrum. And the hotter it gets, the more and more energy comes out. So here are three curves. So something that's 3000 degrees Kelvin will have an energy curve here. And this is wavelengths of light. So these are the down to the right here, shorter, less energetic wavelengths. This is deep infrared, probably even into radio spectrum. And then you start getting, it starts emitting a little bit of visible light, but most of the energy that's being emitted is still into the infrared, into the radio. You get 4000 degrees, you start shifting more into the visible regions. The 5000 degrees Kelvin, this is similar to our star. The surface temperature, or the effective temperature, is what you use in terms of black body radiators, is about 5300 degrees Kelvin. As you see, this star emits most of its energy in the visible region of the spectrum. Not coincidental, that's why our eyes are sensitive to it, because that's what our star mainly emits. And it still emits a lot of infrared. As we know from being sunburned and things like that, it does give out some UV rays as well. And if you got hotter and hotter and hotter, stars like the O-type stars that light up the trapezium of the Orion Nebula, they emit most of their light over here in the UV spectrum. So just kind of remember this, because this is going to be somewhat important. And again, stars range in temperatures. Like I said, our star, a yellow star, it's kind of the cool range, is 5000. But if you look at a lot of variable types, these old H stars, they're closer to 3,000, some even down into the 2,500, 2,000. They're very shifted into the redder parts of the spectrum and into the infrared. So what we're doing when we talk about a photometric magnitude is, I named Johnson originally, then it was expanded on by Cousins, came up with a system where he broke up the spectrum mainly in the visual parts of the region. He did move into the infrared with the I filter, into the UV with the U filter, but he divided up the spectrum with filters with different pass bands. And this is basically doing some really low resolution spectroscopy, because it can tell you different things about the star. Two concepts that we use a lot in astronomy is the term of the magnitude, which is a flux or an intensity of a light. And if that flux is measured into a specific band, we designate it into that band, as you can see, because stars do emit radiation at different wavelengths, or at peaks at different wavelengths based on its temperature. So we kind of cut that up. If you do, the total energy by the star would be, if you do the math, that would be the area under the curve. If you give a measurement of the entire energy being emitted to the star, that's referred to as a bolometric magnitude. It's not used a lot. It's not obtained, observationally. Those bolometric magnitudes tend to be mathematically derived through models from different parameters or different magnitudes that different bands that you might measure by spectra, or there's different ways to come about it. So we divvy up the spectrum. We can measure intensity of the light in different regions of the spectrum, and that tells you different things. So that's the magnitude. And then the other concept is the concept of color. When astronomers talk about the color of stars, what they're talking about is really color indice, and that's two magnitudes that are subtracted to each other from each other that tells you information about the star. By far the most common is B minus V. That's Johnson B band, or blue, minus V, which Johnson kind of called it V to be the visual magnitude, is what he was trying to go for. He was trying to emulate eye response. Now, there are other photometric systems that are come out. I think Johnson is kind of, is still used widely. It's one that's been around the longest. It's very much being replaced by the Sloan photometric system, which has only been around from the 90s. It was designed for the Sloan Digital Sky Survey, but has some advantages and disadvantages, and I think that's where the industry tends to be going. A little off topic there, but the reason B minus V is important, because from that measurement, if you measure a star's magnitude in Johnson V, measure it in Johnson B, subtract those two, B minus V, you get a number, and from that you can tell the temperature of the star, surface temperature. It works well for most stars. It doesn't work as well for some redder stars. They use other indexes or colors, typically for things like Miras that are in the infrared. You'll see J minus K is a common one there. But there's all these different indices that tell astronomers different things about the star. So again, just measuring. What are you doing at the telescope when you're measuring? If you're taking a photometric, here's one of my images. It's a stacked Johnson B image of RZ Cygni. And so I take my target, I take different comparison stars, I measure an instrumental magnitude with my instrument, basically counting photons or counting the flux. Do some math to compare the flux of known sources, and from there I can derive a magnitude in Johnson V. With your, what I like to call the EYE band, or I band, EYE band, you're doing similar things, only you're not doing math involved. Instead of directly measuring photons, you're making comparisons of the brightness of your target to other pre-selected by people who know how to select good comparison stars. There is some art to it, color being a big factor. And you're making those comparisons similar to what a CCD does, and driving a magnitude from it. But you can be led astray if you don't really understand what's going on. So like I said, most variable stars will get the HR diagram up a little later, tend to skew much to the red. So here's a typical black body profile for most long period variables, your Myra stars, which are good for SRAs. These kind of stars tend to range from 3,200 degrees to about 2,000 degrees from some of the cooler carbon stars. As you can see from the curve, most of that energy is rated in the infrared, where your eyes just are not sensitive to. The Johnson eye band filter cuts out at about 1,000 nanometers, so it catches a lot of the energy. But it does emit, they do emit in the visible, but that's not where most of the energy is. And if you look at this curve where the visual region is a star that's 3,200 degrees, it's going to put more out in the redder regions, or have more intense light flux in the redder regions, and it starts to dip down as you start to get into the yellow to the green, and then almost nothing by the time you get to the blue. So what does that tell you? It tells you if I'm measuring a very red or very cool star with a Johnson B filter, that magnitude is going to be a lot dimmer than when I measure it with a Johnson V filter. It's definitely way lighter than if I used Cousins R filter. How does this relate to your eye? So your eye acts like a filter similar to these Johnson Cousins filters, because you are sensitive to only a certain wavelengths of light, and the stars is emitting in much other wavelengths that you just can't see or not sensitive to. So I've lined these up. This down here, this is a typical eye in typical eye performance. You see there's two curves here. It's because your eye does not always respond to, at all times. It's not always going to be the same. So I did my best to line up these scales. So here's 450 nanometers, 45 here, there's 450 nanometers, 600, 6,000 angstroms, 600 nanometers equal. So what happens is, your eyes are composed of both rods and cones, and depending on light levels and color, you'll be in a different type of response zone. So as your eye starts to dark adapt, your rods start to subside, and your cones are more in control of what's going on. They are more sensitive to bluer light. Also, when you're looking at very faint objects, you're more into a cone type response, which again skews a little further to the blue. This came up for me when I first started out because, well, let me back up. One of the questions I asked in the forums was, okay, would you expect, if you went out and visually measured a star at the same time as you were taking an image with a CCD with a Johnson V filter, would you expect the magnitude to be the same, or would they be different? And so the answer really is, it depends. If you're looking at a very yellow star, typically like our star, say with a color index of B minus V plus 5.5, and your eyes were not dark adapted, you absolutely would expect them to be about the same. The eye response would be very much similar to the Johnson B filter. Now, if you were dark adapted, your eyes were dark adapted, your response would shift further to the blue, and you would actually visually see that star a little dimmer than you would in your camera with your Johnson V filter. So it would shift down. Now, this effect also happens, say if you're dark adapted or not dark adapted, if the star is very red. If stars that are very red, your response is better. You can see the better part of the blue than the Johnson V filter. So if you have a very red star, you would expect somebody who's measuring the star with their EYE filters, their eyes, to actually be shifted a little bit more to the blue. And we'll see examples of that. I hope that makes sense, but we can definitely see this. This is, what star was this? This is our LEP. This is one of the reddest stars out there. This is Hen's Crimson Star in Olympus. So you can see here, you know, we consider red when B minus V is greater than 1. You can see here, this, I took these measurements. I didn't take these that are kind of off, but these are all me. These are pretty much all me. Red stars can be tricky photometrically. So if you look at V is, let's say 8, B is 13.5. So B minus V is like 5.5. That's insane. Like I said, red is considered greater than 1. Greater than 2, there aren't a whole lot of them out there. They're out there. Here's one of them, but this is one of the reddest stars. I'm sure most of you have seen it. If you don't, we got to wait till winter time. Go check it out with your binoculars or something. It's really cool. But here, if you look at, here's my Johnson V measurements, pretty consistent. Here is the average visual observers. As you can see, they're tacking about almost a magnitude in most instances dimmer in compared to the V band. This is what I would expect because of eye response. It's going to be somewhere between the V and the B filter, closer to the V. This is a relatively bright star, so you're not as much into your cones. Like if this was a dim star, I would expect it to shift it further to the blue. But because it's relatively bright, but because of its red color, this is what I would expect. Now, if you look at something like P Cygni, it's hard to find really kind of white to blue variable stars. There's not many out there. So this is P Cygni. This is an Escherichia star. They're extremely rare. These are some of the biggest, brightest stuff out there. And the reason that they're variable is because they're so large. It's nothing intrinsic like a Mira that's pulsating. It's just so large that the surface is unstable, which is caused, well, I guess it is pulsating because of it's unstable, different mechanism. But if you look here, I mean, it looks like a big shift like the other one, but look at the scale. Now your V filter is shooting 4.8 and your blue filter is shooting 5.2. So instead of B minus V being 5.5, and this one we're talking about like 0.4. Now, I couldn't find a good example, unfortunately, here. Most of this, the reason that if you get to really blue stars like this, intrinsically, the blue filter would actually be higher than the V filter. Again, it's rare because there's not that many of these really bright blue stars, but this star is so far away that there's a lot of dust in between us, which is reddening the light a little bit. But be that as it may, if you look at the average visual observer, the visual average is pretty well tracking the V filter. Again, this is a bluer star. It's a very bright star. This is exactly what I would expect, like I was saying before. Yeah, be similar to the sun. So the eye response is very much tracking the Johnson V filter. And these are the conditions that you would expect that, just as these are the conditions that you would expect you to be more shifted to the blue. So again, you just got to kind of be conscious of what's going on. Here's another red star. This is more typical red for, this is our cap. again, these are my measurements. These are the Johnson R. These are the Johnson I. Here's the V filter. This one's interesting. This is all the same observer. Only one guy's been doing visual observations. And this is about a 3-month period. And here he's pretty close to the V filter, and then it drops down. What I suspect is happening here is he was observing while not dark adapted. And here probably was dark adapted. And that's why you see the greater difference there. So again, I talk about red stars. Most of the variables you come in are pretty red, widest stars variable. For those who may not, sometimes I forget, I throw HR diagrams and just assume people know about them. But if you take it, any astrophysics 101, this is where you start, was with the HR diagram. Its plot on the left is, well, it could be a couple of different things on that horizontal active that are similar. It can either be absolute magnitude, intensity, luminosity, and then on the bottom axis could be spectral class or temperature. So the stars to the left are the hottest, stars to the right, they get cooler. The stars down at the bottom are the dimmest. You go up, they get brighter. 90% of stars are here on what's known as the main sequence. These are your hydrogen burning. The stars are just in their adult life, workaday life. And they spend 90% of their lifetime there. 90% of the stars are there. They spend 90% of their life there. When as they age, things start to happen. So stars like our sun start going up this evolutionary track and get into the giant phase. And this is when they start becoming unstable. They start pulsating and they become variables. Or if they're really big over here, nice and blue, they come across straighter. And as they move into this yellow region, it's when I drew up real quick to kind of see the different types of regions where you see different variables. Here in the yellow series, you use your Cepheids. These are the larger stars that are evolving over. RV taus, super giants like Betelgeuse, and then your red giants. This is where you find your Miros and things like that as they get out the asymptotic branch. But again, if you look at down here, they list color index B minus V. Most of these are in the 0.8, 0.9 or greater redness, and then as they really age and get into the carbon star phase, it gets even greater. So a lot of people say there are intricacies and things you have to understand, especially if you want to check yourself in light curve generator. Just because you're not on the Johnson V filter, I've seen people freak out like, oh no, my visual measurements aren't aligning with the Johnson V CCD guy. Well, there may be a reason for that. It may be that you're absolutely right, and it shouldn't be with the Johnson V. And also, just don't take photometry for the gospel. It's another pet peeve of my people go, well, photometry has to be more accurate. There's a lot of bad photometrists out there, unfortunately. And a good visual observer can be a poor or mediocre photometrist as far as accuracy and precision, if they know what they're doing. So is that all I got? Yeah, that's all I got. I probably rambled a little bit more than I anticipated, but hopefully you took something from it. And then if you have any questions, post them in the forum and I will do my best to answer them. And I'll catch you all later. Bye.